Hello and welcome again to another episode of Sacktown Talks. Today we have a special show. Joining us is Dr. Marty Ralph, joining us from the University of San Diego Scripps Institution of Oceanography. Dr. Ralph, thanks for joining us. How's it going?
Going well. Thanks for taking the time on this.
Yeah, you've become pretty popular here of late. I remember a couple of years ago hearing the term atmospheric river. Sounded like a sci-fi movie, and now we hear it, day to day here on our weather channels. Kind of, how's it feel to finally have this notoriety of the atmospheric river expert?
Well, the thing that's good is that the atmosphere is organized to transport water vapor in these storms. It's just how it works, and it's good to see people recognizing and understanding the important role atmospheric rivers play in our water supply and our flood risk. So it's super good to see it catching on.
Yeah, I guess for our listeners at home, can you kind of give us a little bit about your background and how you kind of got into studying these atmospheric rivers?
Yeah, sure. I'm a meteorologist, and I got into it because I moved from suburban Detroit to southern Arizona back in the 1900s. And it was a totally different world. And the rain fell and the desert bloomed and the rivers flowed, and I just got hooked. And ever since then, I've been sort of familiar with the Western water issues and seeing in meteorology how much more there is to be done to try to help out providing better information. So these storms really became a focus of my attention almost 20 years ago now, when I realized a study from MIT back in 1998 had identified them as a phenomena, and I realized, the light bulb went off. Wow, this is what I've been studying the last few years, and it just really took off.
Interesting. So currently you're working with the Scripps Institution of Oceanography and the Western Weather Center. Kind of what kind of work are you doing there, and what are you guys working on?
Yeah, I left NOAA, the National Oceanic and Atmospheric Administration, back about 8 years ago to start the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography, specifically to try to build new tools and information and knowledge for Western water managers. And atmospheric river storms are the main thing to study.
And kind of, what I guess for us at home, like, what is an atmospheric river, and kind of how do you define that?
Yeah, so an atmospheric river is really essentially a river in the sky, but it's a river of water vapor rather than of liquid. If it were if you wanted to compare it with, say, the Mississippi River, it's much wider. It's like 500 miles wide and a couple thousand miles long, but only about 2 miles, 3 miles deep, 2 miles deep. And yet, if you slice across an atmospheric river and calculate how much water vapor is flowing along it, it's about 25 times the Mississippi River on average. So it's a lot of water vapor, and there's only 3 or 4 of them present in the Northern Hemisphere at any given time normally.
So are these atmospheric rivers just constantly kind of going overhead, or I guess, can we follow them? And I guess, is there a way to, make them come when we need them?
Well, we can't control them, but we can observe them now. Satellite data, and we're using aircraft data now, and weather prediction models and climate models. They have you can see ARs in the data, and we're learning how they work, how they're structured, how to where the forecasts go wrong, and how to improve on that.
And then, for probably like 20 years ago, we only hear about El Nino or La Nina here in the area. And if it was an El Nino year, we knew it was going to be a wet year. If it was a La Nina year, we knew it was probably going to be a drought year. Kind of, how does this correspond, this El Nino and La Nina phenomenon correspond with atmospheric rivers?
Yeah, that's a great question. And in fact, the El Nino La Nina phenomena is really important. It represents how the ocean conditions in distant parts of the planet, away across the Pacific and even in the Indian Ocean, can influence the weather in North America. It does so by changing the storm track overall. But what we've found, to our surprise, is that it doesn't really modulate atmospheric rivers as much as we thought it would. And instead, atmospheric rivers are sort of the disruptors of the relationship we would otherwise expect between El Nino, La Nina, and rain in Southern California, let's say. So because atmospheric rivers, if we get a lot of them, we get a wet year. If we don't get enough of them, we get a dry year. And if it goes on a couple of years, we slide down into drought. a single atmospheric river, a big one, can really make or break a water year to some degree. So the La Nina, El Nino thing, it's more like adjusting the odds of getting wet or dry. And it's the ARs that are really delivering the wet or dry.
You know, I know this is something you've been working on, and it kind of explain to our viewers how the study of atmospheric rivers is important to kind of managing our water here in California.
That's right. So there was a really key study by Kane and Dettinger a few years back that showed, like for the Sacramento, San Joaquin River basins, basically the water fountain of California. If you look at the annual precipitation there, and how that's varied over the last century, what you see are these big wet periods, and then between them, very dry periods, the drought. And if you just take the top 5% wettest days out of each year and set those aside and look at them, and then look at the remaining 95% wet days, those 95% wet days hardly vary at all from year to year. We sort of can rely on that. It's these big wet days that vary a ton from year to year. And they explained 85% of the variability year to year in annual precipitation in this key part of the state. So it really boils down to ARs make or break, the water supply and flood risk for California.
Yeah, I think it was it late October? There was a big storm here mixed with the atmospheric river. What was it called? Something like a water bomb or something like that.
Oh my gosh, you're bringing two completely different things together.
But didn't that happen? Wasn't there some sort of a storm a couple months ago that combined these two forces?
I can explain that. So first of all, since we're talking about atmospheric rivers, I'll start with that. So we had what we now know was a AR5. We have a scale for ARs now, 1, 2, 3, 4, 5. 1 and 2 tend to be mostly beneficial. They produce a lot of rain, but not like the big flooding ones usually. Mm-hmm. ARs 4s and 5s can create a lot of damage if they hit a wet environment, a place that's already saturated and has built environment. So it was an AR5 that hit Central California and Northern California. It actually broke the all-time daily rainfall records for Sacramento and for Santa Rosa, and I'm sure a few other places. Because it came on the heels of the drought, it mostly saturated the soil, which sort of refilled that natural reservoir itself, so that when future storms came, we'd get more runoff into the reservoirs. Now, the bomb thing you're talking about is interesting. So the atmosphere is organized in a way that, just a little bit of background here. You have the cold pole, right? North Pole's cold, right. The equator's warm. That creates a form of potential energy in the atmosphere that if you get a little disturbance form up, it can grow, and it can take that potential energy of the temperature difference and turn it into kinetic energy of wind. And that wind moves water vapor around, and it helps form the atmospheric rivers. So the development of that eddy, which we call a cyclone, involves changing the sea level pressure. So it's like a low pressure center is what develops. And in meteorology, that's been a focus of work for a century. And there's a thing called a bomb, which is when that cyclone forms very quickly. It deepens, we call it. The low pressure becomes lower very fast, and that's called a bomb. And it turned out that storm in October, a bomb cyclone, which is jargon that comes out of the nor'easter thing back in the East Coast. The bomb cyclone off of the West Coast was present in association with this AR hitting. But unlike what people tend to think is that the bomb cyclone formed first and then the AR was steered into California, what happened in reality is there was already an AR5 out there where the very first seed of that cyclone started. And because the AR is basically a ton of water vapor feeding into that cyclone before it develops, it fueled the cyclone to deepen more quickly and actually helped it become a bomb. So it's really a more complicated thing where a pre-existing AR helped create the bomb cyclone, and then the bomb cyclone was present, and the AR ended up coming through and hitting California.
Interesting. Kind of as technology's kind of improving, and you guys are studying more and more things on this issue, kind of how far ahead of time are you guys able to identify these atmospheric rivers and predict, I guess, when rain's coming?
So predicting ARs is, we're lucky to have capability to do that, thanks partly to satellites, to ocean buoys and to complicated, very sophisticated modern weather prediction models that use supercomputers. So we see evidence of ARs coming up to a few days ahead. And when they get within, say, 5 days, we start to really pay attention. And then it still might not be clear whether it's going to hit Northern California or Southern California. But then by 3 days out, we sort of narrow in, oh, it's going to be Northern California. Then a day out, it's sort of like it's going to be the North Bay versus the South Bay, that sort of thing. So we see indications 5 days to 7 days out sometimes. And sometimes we see indications as far as 10 days out, but a lot of times those signals are noise and it looks like there might be an AR coming, but no one shows up. Or we don't see one 10 days out in the forecast, but one shows up anyways.
And I guess, are you able, days ahead to decipher whether it's, a 1, 2, 3, 4, 5?
We do have forecasts that tell us what it's likely to be, but those forecasts have errors in them. So for example, the AR5 that hit the Bay Area, about 2 to 3 days out, the numerical weather prediction models showed us there was about a 30% chance that would become an AR5. There was also a 30% chance it would only stay as an AR3. So we look at, in weather prediction now, we use odds of things happening a lot more than we used to. And in this case, we see the odds changing as the storm gets closer.
Right. A big concern, here in California, especially the last year, has been the drought and kind of how we manage our water and how we can improve, I guess, our storage or our water in the future. Kind of, studying this and kind of knowing the history on this, kind of what do you see for the future of California for our water resources and kind of how to best attain those?
Yeah, I'd say there's 2 background things I want to mention, or 3 really. One is that with the warmer climate, there's going to be less snow in the Sierras. And that's a big natural reservoir for the state, not just the Sierras, but Shasta and all around. So that's going to change the circumstances for which, we have to have water available in the summer. For a long time, there's been enough of it in the winter, usually, to get us through. But that's going to be changing. There's going to be a lot less. So that's one change. Another is because the atmosphere, when it's warmer, can hold more water vapor, it means a warmer atmosphere. And because water vapor is the fuel of an atmospheric river and the fuel of precipitation, the warmer temperatures are going to lead to some atmospheric rivers having more fuel and being stronger. So the very wet days are going to get wetter, is what the models are showing us, meaning maybe the floods are going to get bigger. And yet at the same time, the dry periods between the storms are going to get longer. So essentially the droughts are going to get drier. So we have that sort of swinging between wet and dry is going to be more extreme in the future. And it's already been happening in the last decade, ever since we started our Center for Western Weather and Water Extreme. Now, how we handle that, we think there's a way we can help the state and the region deal with these issues. And it's through something called Forecast Informed Reservoir Operations, FIRO. I'll pronounce it FIRO. And that's a project with the U.S. Army Corps of Engineers and California Department of Water Resources and local water agencies to explore in 3 or 4 reservoirs we're working on whether or not we could bring forecasts of atmospheric rivers into the decision-making at reservoirs to allow more flexibility than they've had historically. Normally, after a big storm, a reservoir that has what's called flood control space, like empty space, so it can take the top off a flood,
right,
it holds back some water, so the flood's worse down, or not as bad downstream. But then they're supposed to release that water quickly afterwards. Well, now with the use of forecasts of atmospheric rivers, we've shown that it's possible, at least in one of the reservoirs we've worked on, or 2 of them really, that it's safe to hold back some of that water if you watch for the forecast of ARs every day. And if you got one coming, then you can release that extra water before problems arise. And that looks to be very promising as an option to adapt to climate change, where FIRO, fueled by atmospheric river forecasts, can have the possibility to help reservoir operators save some extra water after a big storm, or if there's a super big storm coming, actually release some water ahead of the storm that they might otherwise have kept, and therefore increase flood mitigation capacity. And we're working on both sides of that.
Interesting. And I guess in the concept of storage and kind of, I guess, how to manage, I guess the capture of water, kind of, what are your thoughts on that lines, and how can the study of atmospheric rivers kind of help that?
Oh yeah. So one of the big things in this region is groundwater is a really important part of our water management system. And we work, for example, very closely with Orange County Water District and the LA District of the Corps of Engineers on Prado Dam in Southern California. And that dam is operated in a way where they can get a little bit of water out of it to put into the groundwater, recharge the groundwater. What we're doing with FURO there is showing that it's possible to safely do more of that, substantially more. And so in a way, that's FURO is contributing to keeping extra water behind Prado Dam when it's safe to do so after a storm, and releasing it in a way that it gets recharged into the ground. And that supports what people are calling a flood managed aquifer recharge, MAR, or FloodMAR. And there are a variety of programs and developments pursuing that. And I should mention that we work very closely with the California Department of Water Resources, and they run what's called the Atmospheric Rivers Research Program. And it's supporting the science and improvement of prediction of ARs with an eye towards that helping with FURO and ultimately with FloodMAR.
Yeah. Kind of, I guess with your experience, kind of seeing how the climate's changing and kind of the issues facing us in our future, what do you think are some of the important things that the state needs to do to kind of help, preserve its water and kind of ensure that people have water in the future?
Yeah, well, one of the very important things is, to go into the future eyes wide open, right? The reality is the world is changing. The climate is changing, and the precipitation and snow and runoff are changing along the way. So we've got to make sure that we measure those things. In addition, it's really important to be anticipating what those changes might be. And I understand the Association of California Water Agencies, or ACWA, is establishing an initiative to look more at climate change, or the changes in climate that are impactful for water management in the state. Very good progress there, I think, good idea there. So the science that underpins all of this is vital to have that state of the art. So supercomputer models, better observations, scientists working on the problem, agencies working with scientists to explore what's going on. And then FURO and FloodMAR, I think, are really potent opportunities to use as climate adaptation tools. We're studying the applicability of FURO on a few different reservoirs across the state in partnership with the Army Corps of Engineers and Yuba Water and the State Water Project and Orange County Water District and Sonoma Water. And those lessons are going to help us have a better handle on how applicable FURO is across more reservoirs in the state. But because every reservoir is sort of like a person, they're sort of the same, but they're really different. And we got to respect that and pay attention to the details. And so lessons, we're optimistic about FURO's viability on a variety of reservoirs across the state, but each one requires its own sort of careful assessment.
Right. This year it's been announced that, the governor announced about a $31 billion budget surplus. Kind of what would your message be to any members out there looking to help kind of solve the water crisis and use some of this money to help, study or spend on water issues? Kind of, how would you recommend they'd spend that money?
Well, thank you for the question. And the reality is there's been a lot of planning going into this FURO work and into the atmospheric rivers work and into FloodMAR. And there are a lot of technical things to be worked out to support that. And the atmospheric rivers research program in the DWR is a key plan that's very well thought out with lots of input from many people that's going to move the needle forward for these things. The main concept I'd like to emphasize is that essentially the AR program in DWR helps sort of put the F in FURO, where F is forecasting, because the forecasting is the vital part. And today's forecast skill is good enough to take some advantage and manage water more flexibly. But as we improve the forecast skill, it's very likely we'll be able to increase the flexibility for reservoir operators to use their existing systems. So the ability to invest in improving forecasts of atmospheric rivers and their associated precipitation and runoff, I think, is of vital importance to the state.
Yeah. So far we've had a pretty good rain season. It looks like it's kind of brought us out of the depths of the drought. Kind of how do you see the rest of this rainy season going this year?
Yeah, well, that's isn't that the $60 million question? Well, it's sad to say, I'm an optimist by nature, but the reality is sometimes the spigot sort of turns off in California, and we may start the year very wet, but then it turns dry and we don't really keep up with that. In 2017, we had a year where it broke the record for the wettest year in Northern California. And as of a week or so ago, we were wetter than that year was as of the 1st of January. So we're on track with the wettest year on record for Northern California. But whether that continues or not really is what determines the outcome. So the system is now primed. If we get more rain, that it'll run off into the reservoirs more than soak up in the soil. The snowpack is stupendous, and that represents a good sign for the future. But I think we've got to really keep our fingers crossed that the winter doesn't just dry up, and not totally dry up, but that we get enough rain and snow, to continue to be above normal so that we can restore the reservoir levels to at least normal, and hopefully not get too much and end up in flood.
Right. Well, hopefully you're right. Hopefully things continue going well. And thank you so much for joining us and talking to us about this topic. I know you've been really popular of late and making the circuits. If any of our listeners want to kind of follow up on some of the work you do and kind of check in on the work that you've done, where could they take a look at?
Yeah, if you go to this super nerdy website called CW3E, the letter C, the letter W, the number 3, and the letter E.ucsd.edu, we've got a ton of information on there. And some of it's in very non-technical form, and others are super technical. So take a look on there. You'll see the state-of-the-art stuff going on in atmospheric rivers and in forecast-informed reservoir operations.
Okay, awesome. Well, thank you so much for joining us, Dr. Ralph, and I hope you have a great weekend.
Thank you. You too.
Thanks.
Take care.
Bye.